Okay, welcome everyone to the first University of Texas Energy Symposium for the fall 2021 semester. Today we have Mick Carbajales-Dale, who I'll introduce a little bit more in a few seconds here. But first, just like to highlight some of the talks that are upcoming the next couple of weeks after today, September 7th. So next week, September 14th, we have Brett Perlman, who is CEO of the Center for Houston's Future, is going to talk about oil markets, oil prices, and how they relate to the Texas economy. September 21st, following that, we'll have Imre Gencer from MIT Energy Initiative. He's a research scientist there, and he's working on models, perhaps maybe similar to what Mick discusses with us today, navigating an energy transition through the framework he calls the Sesame model, or Sesame framework. And after that, we'll have a distinguished lecture series, a discussion sponsored by the K. Bailey Hutchinson Center for Energy Law and Business, a little discussion on energy transition again. So we have a lot of things here at the beginning of the semester on the concept of energy transition and economy. So it's a pleasure here today to have Mick Carbajales-Dale, someone I know from a few years now, maybe even a decade, I'm not sure. He's going to talk about some of his modeling, in particular his BaSKET modeling, building a strategy for key energy transitions. He's an assistant professor in environmental engineering and earth sciences at Clemson University. Further on his background, he got his PhD at New Zealand and worked as a postdoctoral fellow at the Global Climate and Energy Project at Stanford before he went to Clemson University, performing various kinds of systems type assessments, life cycle assessments, and understanding the integration of energy into manufacturing and the economy. So his abstract here says, as it says, he's trying to understand and model and test the hypothesis that interacting agents are able to collectively manage a resource transition from non-renewable energy sources like fossil fuels to renewable energy systems. So with that said, we'll now pass over to Mick. We'll stop sharing my screen to pass over to him. Remind everyone to submit questions in the question and answer or Q&A feature of Zoom. You can ask questions at any time, and please type questions at any time. If there are clarification questions that you type in, I can try to interject at the time and clarify as he goes through his presentation. Other than that, we'll take questions at the end of his presentation. So with that said, Mick, the floor is yours.
Well, thank you for the introduction, Gary, and thank you also for the invite. It looks like you guys have a great lineup for the semester, so I'm very honored to be kicking you off here. As Gary said, my talk today is building a strategy for key energy transition. So this is the BaSKET model. Just before we begin, I want to say that as I was talking with Carrie just a second ago, unfortunately, as a professor, I don't get a lot of time to do a whole lot of research. And so I want to give a shout out to my research group. And you see a bunch of my students here. And in particular, this one, John Sherwood here, who basically this is the work that he did throughout his PhD. So this was kind of the main focus of his PhD. But as a lot of successful, I guess, PhD or hardworking PhD students, he actually produced a lot of papers on a lot of different topics. So unfortunately, this work is not as well developed as we would have liked, but I'll show you kind of the limitations and then where we want to take it into the future. Okay, so just an outline for the talk I'm going to give you today. We're going to have some motivation for why these types of models are important. And I think hopefully you guys here, it looks like you're talking about energy transition for this semester. So hopefully you're pretty much sold on the idea that this is important anyway. I'm then going to move into some background. The kind of field that both Kerry and I work in is called Biophysical Economics. So I'm going to explain some of that and some of the models that you find in that discipline. I'm then going to talk over the BaSKET methodology. So talking about some key assumptions and then talking about the structure of the model. And then going to present some results and then talk about conclusions and future work. Okay, so in terms of motivation, this is from the IPCC latest AR6 report that dropped earlier this month or just last month. And basically now the IPCC is pretty categorically stating that climate change is real. It is undeniably caused by human activity. They're making very strong statements about this now. And the thing to remember is that the IPCC is primarily scientific, but it's also a group of governments, right? And so everything that comes into those reports has to be signed off by the members of those governments. And so if they make very strong statements like we are absolutely certain, then that means that those governments have signed off on that. So that's a strong statement indeed, about as strong as you're ever going to get from this kind of report. Basically saying that human influence has warmed the climate at a rate that is unprecedented in the last 2,000 years. So here you see these last 2,000 years. I don't know if you can see my cursor, but the plot on the left there is the last 2,000 years. And then this little sliver on the right between 1850 and 2020 is then blown up in the graph on the right. And we can see the divergence between what we think would have happened had humans not gone through the Industrial Revolution, started using fossil fuels and emitting those carbon dioxide and other greenhouse gases into the atmosphere. And then so clearly, if we are changing the composition of the atmosphere, increasing those greenhouse gases, then we can expect to see some impacts from that, including temperature change. So here they're plotting out potential projections of temperature change over the next century. And so these SPCs are shared socioeconomic pathways, and I'm going to talk a little bit more about what those mean a little bit later on. But essentially, they kind of divide into 5 different families. So we have the kind of more sustainable paths you see at the bottom, where they think we can limit to below 2 degrees warming, or the more, what you might say, business as usual or high growth, high impact scenarios where we could see as much as 5 degrees Celsius warming. And obviously all of that warming will have other impacts. So things like mean sea level change. So here they're plotting that out over the next century. We could see as much as 1 meter of global mean sea level rise. And then in fact, if you keep on going out to 2300, as this bar on the right shows, the plot on the right, then it could be as much as kind of 3 meters, or even, they say, under the kind of direst scenarios, we could see sea level rise greater than 15 meters. So they cannot rule that out. So that's just a horrific, kind of catastrophic, cataclysmic even scenario to think about. Okay, so that's kind of thinking about climate change. So that's one aspect of, we need this transition towards a low emissions electricity grid, energy sector. Another motivation is from thinking about resource criticality. So here we see a reworking of the periodic table from Gradle et al. And basically here they've kind of colored the different elements by their ability to be substituted in the technological processes or technologies that they often get found in. And I'll give you a quick example here. Well, sorry, let me just say that if they're on the red end, then it's very difficult to find adequate substitutes for them. If they're more towards the green or blue, then the potential for being substituted is possible. And so here we're going to take an example of rhenium, which is used in applications like this. So high temperature, it has a very high melting point. And so it's used in high temperature applications. So like this gas turbine, I guess, here. So obviously that has applications for thermoelectric power generation, either through fossil fuels or nuclear, as you might find at the bottom, or even in renewable applications. So this is the Ivanpah solar farm over in California, which obviously has high temperatures and so needs things like this, like rhenium. So notice that term there, substitutability, is often what we think about in terms of economics. We talk about substitution of different technologies or materials within technologies. And so part of this exploration is thinking about that. How possible is it to substitute? How quickly can we do that? We can kind of expand on this idea of criticality. And here, this is from Glöser et al. And they think about two dimensions of this criticality. So here on the horizontal axis, we have supply risk. So how likely is it that the supply of a material might be disrupted? And then on the vertical axis, we have vulnerability to supply restrictions. So if the supply of a material was restricted, what might be the impact? How bad could it be? So that kind of factors in that substitutability. And so then obviously we would prefer to be using materials that are kind of down towards the bottom left here in section 1. But here you see them plotting all of the different, or not all, but many of the different materials that we use in our kind of highly technological complex societies. And you can see that rhenium, for one, is up in that top right-hand box, that box 5. But yeah, many of these materials that we use have some degree of either supply risk or kind of vulnerability, like impact, supply risk impact. Within the EU, they're very big on kind of thinking about supply or resource constraints. And so here we see this kind of idea taken a little bit further. So thinking about the specific technologies that might be impacted by these different kind of groups of materials based on their supply risk here on the left. So then which technologies those materials flow into, be it batteries or fuel cells or wind turbines in the middle here, and then which sectors of the economy rely on those technologies. So clearly something like traction motors in the middle here, kind of fourth from the top in the technologies, is very dependent on rare earth elements. So that's going to have big impacts for kind of the future of battery electric vehicles, for instance. Okay.
Make clarification on referring to the last slide. Just what do you have examples of supply restrictions? Or supply.
So that would be something like this. So thinking about rhenium here, the fact that the reason that it's used in these applications is because it has a very high melting point, right? So on this vertical axis, it has a high, it's around about 0.8, I guess, because you can only substitute it with things that also have high melting points. So tungsten, for instance, or maybe you can develop some material that has a high melting point, right? So it's basically, it's some measure of their substitutability within the technologies that they use. Does that make sense?
Okay. Yeah, thanks. I think they're trying to clarify supply risk versus restriction. So yeah.
Sure. Yeah, and then supply risk would be things like, are all of these materials, is that they're just one country that controls the supply of these materials, let's say, or is supply dominated by kind of geopolitically unstable areas? So maybe there were mines in Afghanistan. What happens to those mines now that the US is withdrawn? That kind of stuff, right? How likely is the supply to be disrupted? Okay, good. So I hope that I've convinced you that there's some motivation for thinking about these transitions, both in terms of something like climate, but also in terms of our consumption of non-renewable resources. And we can kind of lump both of these under this issue of resource constraints, right? So on the climate side, that resource is our ability to keep putting carbon dioxide into the atmosphere. That is constrained. On the other side, it's our extraction of resources from the environment, which is constrained. Okay, so moving on then to a kind of discipline or frame in which we can think about these kinds of issues. As I told you before, the field that I work in and Kerry works in as well is biophysical economics. And I'm gonna explain what that is by contrasting it with more traditional or neoclassical economics. So here we see an image that is familiar if you've ever opened up an economics textbook. It's kind of the circular model of the economy, where we have society on the right here and the economy on the left, so sometimes called consumption and production. And basically what happens is society provides the economy with factors of production, so things like capital or labor, and the economy buys those things and supplies income back to society. So wages for labor, for instance. And then the economy produces goods and services, and society pays for those goods and services, okay? And here you can see that kind of circular flow, or these two kind of opposite running flows of, in the one hand, goods and materials, and the other is kind of financial spending. But what you notice is that this is kind of floating off in the void. Basically, this is a perpetual motion machine of the first kind. It produces work without any inputs of energy, right? So it's violating the first law of thermodynamics. I hope as folks interested in energy, then you're all familiar with the first law of thermodynamics. Basically, you can't get anything for free. And so biophysical economics would say, well, we need to ground this whole thing in some biophysical reality. And so we extend this picture by adding in this biosphere here at the bottom and saying, okay, we need energy resources coming into the economy by which those goods and services are being produced, right? So this sort of thing has been done. So based on the kind of oil shocks of the 70s, then people really started to take an interest in energy. The International Energy Agency was formed. And this kind of moved us away from this kind of idea of the economy as a clockwork or, kind of clock flowing thing to more like a machine model of the economy, where we had to fuel the economy essentially. And we still talk about that, where we talk about things like economic growth stalling out as if it's a motor, right? The issue with this framework, although it's better than the previous model, it's now a perpetual motion machine of the second kind. So it violates the second law of thermodynamics, which says that basically for any system to work, it also needs to export entropy. And so, I've lost my thing here. Okay, yeah. So basically we need to add in these other flows here. So the first thing we need to add in is we don't just need energy resources coming in from the biosphere, we need materials coming in as well, right? If we're going to make a car, we need the things to build the car with. So the steel and glass and all that kind of stuff has to come from raw materials. And the second thing is that the economy, both the economy, but also society, produced wastes. And those have to go back into the biosphere. So straight away here, you can see the kind of context in which things like climate change or resource constraints are happening, right? we're taking too much stuff from the biosphere, or we're putting out too much waste into the biosphere. So faster than the biosphere can assimilate either that resource extraction or the dumping of those wastes. And so that leads us to issues. And so from a biophysical economics perspective, we have these kind of three different eras. And this is what we talked about in a previous book called Beyond GDP. So basically, the clockwork model of the economy came around in the period, I guess, from the start of the Industrial Revolution up until maybe the 1970s. And this was definitely an era of abundance, where the major constraint on human activity was having enough human stuff around, right? If you, the kind of constraint on the amount of fish that you could catch was the amount of boats that were going out to catch that fish. As I said, in the 1970s, we came into this era of energy constraints where we realized that actually energy inputs to the environment were pretty important and we needed to start thinking about them. Arguably, within the last, I don't know, 20, 30 years maybe, we've moved into this third era, which is this resource depletion or resource constraints era, when we need to start thinking also about the waste that we're putting out. Maybe the metaphor there is more like a metabolism. So this idea of the economy as an organism, which is definitely along the lines of that work that Kerry does. Or we could think about it not just one organism, but a community of organisms or a supraorganism, right? Okay, so we've talked about what biophysical economics is. We can now think about, well, what sorts of models are used within biophysical economics. So here we're turning to the work that my PhD student, John Sherwood, did. And he took a very engineering approach, I would say, to doing a literature review. He looked out over the main kind of journals that publish biophysical economics type work, and did a literature review of nearly 1,400 papers with some initial screening. Those were reduced to just over 110 that were actually run through his framework, which I'll talk about in a second, this modeling taxonomy that he identified maybe, or kind of created. Okay, so this framework, this taxonomy works on 6 different dimensions. And so the first dimension is framework. So basically, this characterizes the big picture structure of this model type. So running from individual-based models, so the kind of basic unit within a model is an individual. We could have an agent-based model, input-output model, all the way up to aggregate production function. So these are different types of models that you could have, or a modeler could build to try and describe a system. And I do have some examples later which can kind of describe the differences between these. But basically, yeah, so that's that framework dimension. Okay, the next dimension is spatial scale, so ranging from a city scale or smaller up to the entire globe, right? And clearly you can think that this has some connection with that first framework dimension. It's unlikely that you would model the world based on individuals, right? Or alternatively, it's unlikely that you would use an aggregate production function to model a city or a smaller unit, right? The third dimension is this time horizon. So ranging from immediate or kind of no time dimension through short term, medium term, and then ultra long term of 100+ years. So that IPCC modeling arguably lands in this kind of long term to ultra long term. So they look out over the century, but sometimes do a little bit more long term thinking than that even. The next dimension is the kind of ethos behind what the model is trying to do. So on one end, we have pure theory. So maybe they're just trying to just explore concepts without linking to specific data. On the other end, you would have purely empirical models. So maybe you're not even trying to elucidate any theory, you're just looking at the data and trying to kind of let the data drive the type of model that you might construct, right, without any theory. The next dimension is in terms of the origins of the model. So where kind of, which domain is the model coming from? What's its kind of origin story, I guess, if we're thinking about that. So on the one end, we would have physical sciences, so maybe like physics or chemistry. Ecology would be the next one. And then at the other end, we might have like behavioral economics or social science type models. So a thing to note here is that each of these different domains or fields have different implicit or explicit assumptions, and those would constrain the capabilities of their models in different ways, right? So I just showed you an example of that with looking at the kind of traditional economics model of the economy, right? It inherently does not capture the flows between the economy and the biosphere, and thereby is kind of limited in some ways because of that. Okay, and then the last dimension here is this mechanism dimension. And so this kind of stems from the fact that we use this term model in a few different ways, ranging from, on the one end, something like a simulation model, where you have to run the model. We also use the term model in terms of optimization, where there's some objective function that we're trying to achieve. Or another use of model might be kind of regression model, right? So you're just doing some statistical analysis, but there's not really any inherent structure other than what's in the data, right? Were there any clarification questions on the?
Nothing yet here. Go ahead.
Good. Okay, so so just to kind of put it all together, then we have these 6 different dimensions, and the coloring here shows you how many of these 110 papers fell into each of these categories. So the darker it is, then the more papers fell under that categorization. So as you can see, for instance, in mechanism, we have a lot of statistical analysis, a lot of simulation, but not much optimization. On the spatial scale, a lot of papers using models of the world scale, not much at the continent, some country scale, so on and so forth. And then what we can start to do is look at the combination of these different dimensions, and then start to identify gaps within this biophysical economics literature. So here you can see John identified these 14 gaps within the research space. So some of these are fairly kind of obvious gaps. So for instance, you're unlikely to do individual-based models at very large scales, or you're unlikely to do things where you have very short time steps of maybe an hour or so, but at large scales as well, right? So sometimes it's obvious why people haven't produced those kinds of models, just because there's kind of resource constraints on doing it in terms of computational power or that kind of stuff. But what you can see here, we have on the right is lots of systems dynamics models at a global scale, long time horizons. And then there's a mix of theory and empirical, mix of statistics and simulation. There aren't too many agent-based models, and that was part of the motivation for John to create this agent-based models. Yeah, but if you read this paper that John put together, you'll find him kind of identifying these different regions and potential kind of research questions that could fill in those gaps. So just to kind of circle back to talking about climate change and some of the models that we do use in that space, we have a lot of these what's called integrated assessment models. And so here, what these models do is they actually kind of try to combine lots of different models in different domains, looking at different systems into one, as it suggests, integrated model. So for instance, here, as we're showing in this picture here, you might have a model of GDP and how that might grow based on kind of population or other economic factors over the next, let's say, 100 years. That would then be tied with an energy system model, which then, based on trying to meet some level of economic demand, needs to produce a certain amount of energy, and so on and so forth. So I'm going to give you an example of a specific model that's used by the IPCC. So here, this is called the message macro model, named for two of its kind of sub-pieces here. So macro, as the name suggests, is a macroeconomic model. So it takes a bunch of inputs, so population, desired population, economic growth, this kind of thing, and then turns that into what would be the expected energy demand. And then this message model, which for kind of our purposes, in terms of thinking about transition of energy systems, is the kind of important one, I guess, takes that demand and turns that into, well, what are the likely technologies that would come about to meet that demand? And so here you can see what they call the reference energy system, and in black is the 1990, and in orange here is 2020. So this is from a few years ago. But basically, you can see the pathways to get from primary energy, so energy resources in the ground or in the environment, through to final demand, and looking at the different kind of ways that that might happen. So the underlying idea here is that this is based on cost, right? We try and meet this demand at the lowest cost, and who decides what gets built is kind of a central decision maker. So this was another issue that this model was trying to address, is based on that central decision making, then we have a kind of best case scenario where it would appear to be easier to transition because all of the decision making on what is going to get built is just done by one centralized decision maker, or maybe it's done in each region by a central decision maker. Whereas what we have in the real economy is lots of different companies, people making these decisions all independent or somewhat independently, right? Which suggests more that an agent-based model might not have the same kind of ability to shift quickly where decision making is distributed in that kind of way. In the interest of time, I'm going to skip over quickly, but basically these are those different scenario families that the IPCC is using. So ranging from sustainability down in the bottom corner up to based on kind of adaptation challenges and mitigation challenges. They have these 5 families. But something to note is that they don't just use one integrated assessment model. They use a whole different bunch of integrated assessment models, and you can see that those give different results for what the fuel mix in 2100 would look like for each of those different scenarios. So there's different ways in which that kind of lowest cost optimization is being done within each of these different models, but it still has this kind of inherent, all of these different integrated assessment models have this inherent I guess, function, which is this centralized decision making. Okay, so moving on then to this BaSKET model, the kind of key research question that was driving this is, if we have a system of multiple interacting agents, can they collectively manage a resource transition away from non-renewable energy resources like fossil fuels to renewable energy systems, or even a circular economy? So some other things that we think about in terms of trying to reduce our resource use. And so here's the kind of some of the reasoning for that is these energy economy models like the message macro that I showed you have significant feedback loops that are missing. So economic complexities are not incorporated. Technological advancement is poorly modeled, and then the centralized decision-making implies a best case scenario. And I'll talk a little bit, but hopefully those other things should become clear as I keep talking. Okay, so basically a lot of this energy economic or just economic modeling has these 4 assumptions, which this BaSKET model is somewhat designed to try and push against. So the first one is factor substitution. So most economic models assume natural resources or built capital as substitutable inputs into production, and therefore economic growth can work just as well with one or the other, right? We can keep on increasing our economic activity. The cost share theorem basically says that the level of disruption to the economy is based upon the cost share of a resource within the economy. So if we only spend, let's say, 10% of our economic output, our GDP, on, let's say, oil, then oil could never cause more than 10% of disruption if its supply is constrained. The third assumption is that decision makers within the economy have perfect knowledge or foresight, and so are able to make these resource allocation decisions kind of somewhat perfectly. And then the fourth assumption is that there's these representative agents, and they all act in kind of perfect economic rationality. Okay, so I'm now going to explain what this BaSKET model tries to do, but basically it's based on these 4 elements: agents, resources, devices, and trade. So agents do try to maximize their utility through the choices they make. That's in the kind of, what I'm going to talk a lot about is the vanilla flavor of this model, and that's the results that I'm going to show you from this vanilla flavor, where pretty much everything is homogenized. So right now, agents are homogenized. They're no different one from another, except the fact that agent 1 is agent 1, 1 is agent 2, right? That's something that we can start to play with in future versions. So resources, agents get utility through having resources. And again, those resources are homogenized. Again, something we can play with in future versions of the model. Agents can invent devices that speed up extraction of resources, but also require resources to build. And then agents can trade both resources and devices. I'm going to skip over this stuff in the interests of time, but it's basically just expanding more on each of those things. What I'm going to take you through is the kind of the steps that the model takes when it runs. Okay, so the first step is this resource extraction. So agents decide which resource to extract by the amount of utility that it provides to them, and in fact, the marginal utility. And that marginal utility decreases as a function of the number of units that the resource owns. And so if the agent owns more of resource X than it does resource Y, then the likelihood is that the next time it goes to extract some resource, it'll extract resource Y. But that said, extracting the resource takes time and depends on the agent's experience level at extracting that resource. And they gain experience whenever they extract it. And that's modeled by the shape of this curve here. So when they first come to extract it, they don't have much experience, and then they get better and better, and they can extract resources faster and faster as they have more experience with it. The next step is resource trade. So basically, agents are paired together. They rank which resources they have, and then they take their 5 lowest resources and see if they want to trade with the other agent. And that's based on the mean utility that they have. So, and one thing to note is that these trades are just simple trades. They're not trying to kind of scam each other. They're being honest about what they have. The trade only occurs if both agents benefit. And then we do have some measure of price within the model. It's based on agents' valuation of those resources. The next step then is device invention. So initially, agents don't have any devices for extracting. So you can imagine they're just like, I don't know, very primitive person digging in the dirt with their hands kind of thing. And then they can start to invent devices which then enable them to extract resources more quickly. So at first, these are going to be very simple devices. But basically what they do is they need to combine resources to create these devices. So here are resources. And then this tier 1, you can think of like hand tools. So maybe a shovel or a pickaxe or something. That those tier 1 devices are composed of some number of resources. And here we see tier 1 device number 4, which is used to extract resource number 4. Then at the next level, we take some number of tier 1 devices and combine them into a tier 2 device, and then so on and so forth for tier 3, tier 4, however many tiers you want to go up in the model. Okay, so as I mentioned before, this is the kind of vanilla flavor of the model. So all of the resources are the same. The devices differ only in what they're made from and which resource they can aim for. But the things that we can change within the model are how many resources are required to build the tier 1 devices, how many tier 1 devices are required to build the higher level tier devices, and so on and so forth. So then once those devices are invented, then that is the technological recipe for that device. So let's say it's device 4. That's the only one that can extract resource 4. And so that recipe is set. And then other agents can only discover it by purchasing that device and then kind of reverse engineering it. The next step in the model is device trade. So it's very similar to the resource trade, where agents look at the utility that this device is offering them. The difference here is they're not paired randomly, but instead agents are paired with other agents, or they choose which agent they want to trade with based on successful trades they've had in the past. So the idea here is to try and build up these trade networks such that it allows the diffusion of these devices through society. Okay, the next stage in the model is the device production. So agents go into this period of trying to produce new devices, sorry. And this will start with the tier 1 devices, and then they can subsequently use those devices to build higher level tier devices. How long it takes the agent to build that device depends on their experience with building that device, so they get better. So this is trying to model kind of experience curves, that kind of stuff. Okay, and then the last Oh, a point to note, agents lose proficiency at things that they haven't done recently. So that could be device production, but it's also resource extraction. So they kind of lose that ability if they don't keep doing it. Okay, and then the last stage is this resource consumption. So kind of at the end of the day, all of the resources, well, not all of the resources, but some fraction of the resources that an agent holds are consumed. And then also the devices kind of wear out either through their use. So the more they use, the more they wear out. But even if they're not used, there's some depreciation that happens. Okay, so, and then obviously we go into the next time step and we do this whole thing again, and we keep going on for greater and greater time steps. So hopefully that's all clear. So let's look at what happens if we run this model. So I think this was done with 24 agents, 24 resources. And here we're showing on the vertical axis, the mean utility of those agents. And then on the horizontal axis is just the time step that the model is in. So the first thing to note here is, so at the bottom, the lowest line here is this, where we don't have any devices. So this is agents just using their hands, I guess, to extract resources. You can see that the average level of utility, or kind of, let's say, GDP or income that gets produced across all the agents is stuck at this lower level, right? We can notice if we allow the first tier devices, so just these kind of simple hand tools, then this kind of higher level of economic activity is available to the agents and their utility can increase. But you notice there's some kind of variability that's happening across agents. And then similarly, if we allow tier 2, tier 3, tier 4 devices to come online, so you can think of those as, so tier 2 might be a kind of simple machine, tier 3 might be a, I don't know, a steam engine type technology, and then tier 4 might be something even more complicated that you can combine that level of complex machines into a factory or something like that. So 2 points to note: as we increase the level of tiers, then the agents are able to extract more resources and get more utility, but the variability, so I guess the difference between a rich agent and a poor agent is broader in those higher tiers or more complex societies. The other point to note is, as I showed, when the resources were getting turned into devices, that by the kind of tier 4, then all of the resources are required for even just one of the devices. Okay, so we have this kind of technological interconnection through this, these technologies, these devices that are being created. Okay, so this is just the kind of straight model run, the baseline scenario, I guess. This is with unlimited resources, so the resources are not depleted when agents mine them. We were then interested in what happens if we take out one of those resources. So it happens to be, I think, resource 8 that we took out, but that's irrelevant really, because all of the resources are exactly the same, other than which devices they get used in or which agents have experience with them. But here you can see, so that resource was removed at time step 600, just because that's the time step by which most of these system or scenarios had leveled out. What you can see is in the no devices scenario, there's pretty much no impact to removing that resource, which makes sense because the resource isn't being used for anything other than just being dug out of the ground and consumed by agents directly. In the tier 1 example, you can see there's a bit of an impact. So the economic activity goes down a little bit when we remove that resource, but then it just gets back up to the same level. As we get to higher and higher tier levels, we see these kind of pretty major declines in economic output, and the time to recover and get back up to the original level that the economic activity was at before the resource was taken away is longer and longer. And here we see a table. So here, the thing I want you to focus on is this kind of crash severity. So what the level of utility was at before the stuff got before the resource got removed, and then what it drops down to. And in the case of the tier 4, you'll note that that's 31%. So there was a crash of 31%. Bear in mind, because there's 24 resources, then the cost share of that resource should be around 5%. So in all cases where you have these different devices on stream, then that crash is much greater than the cost share of that resource, right? And these are just with homogeneous resources. So this is all to do with the technological kind of interdependence of these resources, nothing to do with the fact that this resource has special properties like rhenium, and it has a high melting point. These are just homogeneous resources. Okay, so under these vanilla conditions, as I've said, these advanced economies can be susceptible to severe collapse and lengthy recovery scenarios. Technology and resource interdependence produces high levels of economic output, but also creates these latent vulnerabilities. And then seemingly small disruptions in these networks can lead to cascading collapse and severe drops in societal well-being. I have an example comparison with Cuba, but I'm not going to go into that now. Maybe we can do that during questions. Okay, as I said, this model right now is based on these kind of vanilla conditions, homogeneous resources, homogeneous agents. What we really want to do is begin to model kind of specific specialized resources. So food, agents require food to live, water, required by agents, but also by some processes. And then particularly we're interested in energy, both renewable and non-renewable, that's required by all processes. So we need energy in order to do anything, right? And then also some key materials and thinking about the ways that those materials, the resources are finite and get depleted over time. Or on the case of non-renewables and renewables, there's some kind of limit to their flow. Okay, and I'm going to end there and say thank you very much for listening, and I'm going to ask for any questions.
All right, thanks, Mick. We do have a few follow-up questions here. So question one is just kind of going back to the literature review that you mentioned before, and the question is just about how that was performed in terms of using a certain kind of software, or how did you identify the different properties or topics in the papers? So yeah, any insights on how that kind of a literature review is done or automated?
Yeah, that's a good question. So we didn't use any specific software. We did do we narrowed the scope to just, I think it was 3 different journals. So I think it was Ecological Economics, Biophysical Economics, and Sustainability, and one other, which I'm blanking on right now. And then John put together a rubric based on those dimensions. So he screened, and I'm blanking on what the screening was done to get that from the 1300 to the 100. But yeah, then basically he put together a rubric, and it was kind of his subjective opinion on where it fell in each of those dimensions.
Right. Okay, thanks.
I would suggest reading the paper for more details.
Right. So anyone interested can contact me and I'll hook you up with Mick. So just going back into your model discussion of resource trade, there was just a question for clarifying how resource trade exists in your model, or an example of that.
Yeah, so basically agents are paired at random for the resource trade, and they identify their 5 lowest resources, and it's just based on terms of their mean utility. So pretty much, what resources do I own the most of? Those are the least valuable to me. so it's nothing to do with, oh, how I might be able to use this resource in the future or anything like that. It's just very simplistic. And then, so these two agents, they come together and they look at those, and basically they say, well, this is how valuable that resource is to me. If they're in agreement that they want to make that trade, then they make the trade. And they don't have to trade all five. They can trade some number of them, of each of those resources. I'm hoping that makes sense.
Okay, makes sense to me, but the person can follow up in the Q&A if that works.
Sure.
And here's a question about, I guess, sort of trying to translate real world concepts to your, as you called it, vanilla model, but generic. How would you influence, or how would you input potential influence of political risk, such as access to different resources? What part of the model or would that fall under?
So in terms of access, are we thinking like geopolitical issues?
I think that's the question. Just right, political influence or risk. Yeah. So
okay.
Of accessing a resource, I suppose.
Yeah. So another thing that we're interested in is adding kind of a spatial component to this. So certain areas have better resources or different resources. And then there's also a transaction cost to trading with someone that's further away. And at that point, I think you could put in, I don't know, some sort of political or kind of non-biophysical, I guess, function in there to look at stability. Or maybe it's a function of, so these agents are supposed to represent kind of societies rather than individuals. And so it could be, well, how well is that agent performing, and their ability to then supply resources or devices could be dependent on that, right?
Right. I think the question might have been asked before you showed your last example of the little disruption there. So I guess you can at least, pose a disruption and then see what happens. And if you have it calibrated to the real world, you can have a feel for which material it is and how big the disruption could be. So that sounded interesting. Yeah, I have a question on the sort of applying probabilities for invention in the different tiers. So I'm just a question on how you do that. So, just maybe for the first tier, do you just sort of roll a computational die and say you have a probability of being able to use a tier one device? Is that sort of step one, or what happens?
Yeah, so basically those probabilities are around the invention. And basically, when an agent comes to invent a device, they base it on the resources that they have the most experience with. And so based on how much experience they have with that resource, then their odds of creating a good device, working device, I guess, go up. And this kind of is intuitive. I mean, if someone was spending all day, every day, I don't know, chopping down trees, their ability to make an axe to chop down a tree would be better, let's say. Does that answer your question?
Yeah. Then I was going to go to tier 2 or 3. Do you treat the probabilities different to get a tier 2 versus a tier 1, or tier 3 versus tier 2?
The specific value of the probabilities is lower, but it's kind of the same idea, that it's based on their experience with
So your experience at the lower level influences your experience to get to the higher level, and you can just replicate that concept, I guess, as many times as it seems feasible.
So one thing that's a limitation in the model right now is that there's no kind of learning curve to learning to use devices. So you're as good at using the device the first time you use it as you are the 100th time, which I think that's a little bit of a flaw within the model, but should be an easy fix.
Here's another question. I'll try to interpret. I'll say it and then I'll try to interpret, I guess, what I think they mean. So are these quote unquote small events that cause resource effects that extrapolate into bigger problems ever be intentionally caused for a certain effect? So I guess they're saying, some nonlinear effects in the economy, if we don't buy into the cost share theorem, but we think that energy can have a larger impact than its cost share if there's a disruption. ever be intentionally caused for a certain effect? I guess it's a broader question outside of the scope of your immediate presentation.
So within the model, it's completely artificial. So it's exogenous. So at time step 600, we removed resource 4 or 8 or whichever one it was, right? And it's done just to kind of see, well, what would be the effects of that perturbation. So it's completely unrealistic because it's also removed for the rest of time, right? It would be better to model that endogenously, so kind of as the resource is depleted, or maybe there's some way to model a supply crunch or something like that, which would be more temporary. In terms of, is the question, could
maybe
we
something
do
in the
that
real world,
in real life?
Yeah, maybe what's an example of the real world?
You can think of these natural experiments. So like the example that we have with Cuba, which I can try and bring up here. So basically here you can see energy imports. So kind of around the collapse of the Soviet Union, Cuba's oil imports dropped by, nearly 50%, pretty much overnight. So obviously that had large impacts on the GDP. Here we're showing it per capita, but I think it was something like a 30%, 35% decrease in GDP. Whereas they weren't really spending very much of their GDP on oil because they were getting it from the Soviet Union at kind of lower prices. So I mean, yeah, there are these natural experiments which occur, which somewhat represent the example within our model. I mean, obviously, then the oil supply did turn back on to at least to a certain extent for Cuba, and so yeah, it's not quite the same.
Right. Yeah, I was thinking of something like 1979 Iranian Revolution and drop in oil production, perhaps having a disproportionate effect compared to its cost change of the price of oil.
Yeah, and the issue here is kind of having to relearn to do a lot of the things that you were doing before using this resource, right?
Yeah, nuclear power could be an example of the relearning, right? Or we've built a lot of nuclear reactors, but are we having a hard time building a new one, even if, not building exactly the same design? There's another comment in here about chip shortages, maybe related to here, is the microchip shortage from COVID production an example of a shortage at a high tier level that doesn't affect the low tier level much, but say impacts the auto industry a lot. Maybe the auto industry is in between there. I don't know. But,
yeah. So I think, I would say that would definitely be an example, and it'd be interesting to try and take data from that and pass that into the model. And this is the thing, as we become more interrelated within these technologies, then these issues become worse. Like, so as all of our devices become smarter and require more of these chips in them, then any supply constraint in one of these technology pathways can then impact all of the others.
Right. Yeah, it seems like a good. Your approach there, the example with the tiers and the simulation was useful because you can kind of imagine, I don't know, the United States or kind of most industrialized countries as having all of these tiers, and even though they might be impacted more from a percentage standpoint, they probably still have higher capability even with a disruption. It's just the magnitude of the disruption is larger compared to lower level, and it's the less developed countries might be impacted less, but they're still behind the curve, if you will. So that's a nice way to think about it, I think.
Yeah.
And here's maybe the last one. I'm trying to phrase the question here properly. Maybe it's a sensitivity question. How do you address resource substitution tolerance, or do you? I guess in terms of what you presented, devices can get made with certain things, and you took away one, and then the tier 4 kind of came back up. So maybe you can just kind of explain how you think that works, that the rebound after the disruption is maybe related here.
Yeah, so I mean, the model, like in this vanilla flavor of the model, then it's assumed that all resources are kind of infinitely substitutable. So I mean, they differ only in number, or I mean, literal, the number, categorical number, rather than how much of it there is. But basically there's a time dimension to it, which is, well, we now have to redesign. Let's say we lost resource 4, but some of the devices that were mining resource 3 required resource 4. Well, now we need to redesign that device and all subsequent kind of higher level devices in order to work around the fact that we no longer have resource 4, right? So, I mean, there is no substitutability issue. It's just the time that it takes to do that, right?
Right. So maybe that's somewhat of a second law thing. You can't make a transformation in 0 time either, right? So
right.
I did some time. So I'll summarize what I think you said there, just to make sure I understand for the question. Yeah. So your model results you showed, anything can substitute for anything. It just takes time, and so any real world restriction on what a material can actually do or what its function is, in some sense, would just makes your transition slower or the adaptation slower in your model.
Yeah, or maybe not possible at all. Yeah,
right,
exactly.
Right.
And that's part of what we want to explore next by having these kind of specialized resources. Yeah, good question.
Excellent. Yeah. So actually, there is one more question here I skipped over. Maybe we'll end on this one. Can you give an energy? If this is just how you envision your model, really. Can you give an energy transition related example that applies to the tier 1 through 4 modeling, right? So you kind of obviously have this energy transition in mind. What's kind of, I don't know, the best example of the challenge that this modeling can help inform?
Well, thinking about trying to get off fossil fuels, right? I think that's kind of the most obvious example. So a kind of tier 1 device might be the automobile, right? So it uses fossil fuels directly, but a tier 4 device might be our cities and how we've structured them around the automobile, right? And then if those kinds of levels of service are not available, then how do we redesign those systems to work with whatever might be the substitute? Maybe not a good example because battery electric vehicles seem pretty good, but maybe gas on-demand gas turbines, right? Our electricity system is designed to be on demand. Renewables don't seem to work quite the same way. So our grids need to be redesigned to kind of handle that. The fact that we don't have dispatchable power or won't have so much dispatchable power in the future, and how do we deal with that?
Right. I think your example was pretty good. A little, at least made sure to keep my mind open in terms of what the tiers could represent if you're thinking about something like a city or a country, even as opposed to just an individual technology or device. So,
right.
Yeah, that brings in, I guess, social sciences, obviously, and planning other things other than sort of pure engineering or science, hard sciences.
Yeah.
Excellent. So I think we'll leave it right there. And so again, thank you very much, Mick Carbajales-Dale, professor at University of Clemson. I thought it was an informative talk. So thank you again for being our speaker.
Yeah, thank you very much for inviting me.
Okay, thank you.